type of AI algorithms that are designed to generate new content or data instance that look similar in distribution as the data that it has been trained on. So more specifically, given a bunch of training data, for example, images of horses, that's image in RD, and we aim to develop this generative modeling such that we can generate new samples that look similar to the training data. Generate Y that ideally from the same target distribution. Okay, so when I was a PhD student, well, back in the old days, when I learned this task, what I was taught is that you should first use some classical statistical method to fit your distribution using your training samples, and then generate from this fitted distribution. And there are a lot of like classical method to fit this density or distribution function. For example, you can use histograms, you can do kernel density estimation, or you can do fit a mixture of Gaussian distributions. However, the modern generation, when they learn about this task, they think about the state-of-the-art generative models, such as generative adversarial networks, variational autoencoders, or diffusion models, which will be the main focus of today's talk. Okay, so what is diffusion models? First, it was inspired by non-equilibrium server dynamics, and diffusion models have now become the cornerstone of generative AI, where people realize its amazing power in various applications such as image generation, video synthesis, natural language processing, and more recently, the design of protein structures. Okay, so in a nutshell, diffusion models consists of two stochastic processes, one forward process where you gradually add noise to a target distribution and diffuse the target distribution into some, for example, white noise or some prior distribution. This can be standard Gaussian. So you completely destroy the signal in your data and make it like a standard Gaussian distribution, for example. And the reverse stochastic process, which gradually converts from pure noise into some distribution, and ideally distribution looks similar to the target distribution. So we have these two stochastic processes, okay? Of course, transforming the data into pure noise, this is very easy. You just add more and more noise to your data, and eventually the signal will be gone. But converting from a pure noise into some target distribution, this is highly non-trivial. Okay, so it turns out that this task can be achieved once you have access to faithful estimate of the Stein score function. And the Stein score function denotes the gradient of log marginal density. Okay, it means that once you have access to this estimate of the score function, then there are many ways to convert or to construct the reverse process such that each yt here in the reverse process has similar distribution to the xt. Okay, so given this, despite the empirical advancement, a mathematical theory to understand diffusion generative models is still far from being mature. So given the complexity of this problem, people often decouple this problem into two stages or two phases. One phase is, as I mentioned, because score function is really important. So one phase is to do score learning or score matching, where you try to use your data to learn the score function, and this can be learned using, for example, deep neural networks. And the second phase, or the second part, is the data generation part, where you try to generate samples based on the score estimates. Okay, so because developing a theory for diffusion models is is hard. So that's why people thought of decouple this hard task into two phases and try to do them separately. Okay, so in this talk, I will be mainly focused on the data generation part. Okay, so there are two mainstream approaches focused on achieving this goal. One approach is called DDPM, or denoising diffusion probabilities models, where this is a stochastic sampler where so you start from a pure noise. This is a standard Gaussian. And each step, you apply this function psi t to your yt. So this is an iterative approach to your yt and noise. More specifically, this sampler contains two parts where you have a deterministic component and a random component. For the deterministic component, it contains your yt plus this st is the score estimate. Okay, so the first part is purely a deterministic function of your yt once you're given this score estimate. And then you add some random component, a random noise, and then this gives you a yt minus 1. So you start from y capital T, that's a pure noise, and apply this function psi t iteratively from y capital T all the way to y1, and hopefully y1 generates high fidelity samples. Okay, so the second mainstream approach is called it's a deterministic sampler, where the most prominent example is the denoising diffusion implicit models, DDIM. This is based on probability flow ODE, where you again start from pure noise and you apply this function phi t iteratively from y capital T and all the way to y1. This phi t is defined as a purely deterministic function of yt. So you can see that once we are given the score estimate st, then we can compute this function and then generate the samples. Does that make sense? Okay, so these are two mainstream approaches that used in practice. Well, in fact, this from a continuous time perspective, we have a forward process. I have shown you a discrete time version, and it corresponds to a continuous time SDE. And the DDPM and DDIM approaches, they respectively designed from this reverse time SDE, reverse SDE and probability flow ODE, where the probability flow ODE shares the same marginal distribution as the reversed SDE. So that's how these two methods are designed. They stem from this continuous time limits. Okay, so my talk will be focusing on two parts. In the first part, I want to develop some non-asymptotic convergence theory for probability flow ODE. And this is like the DDIM that I have talked about. And the second part aims to accelerate those methods, those algorithms. Okay. Okay, so over this past 2 years, people have made remarkable progresses from the theoretical community towards understanding these diffusion models. And most of the works, where I list some of them here, take a detour by first study the continuous time limits via this SD or ODE toolbox, and then try to control the discretization error and reach conclusion for discrete time diffusion process. Okay, so so one question that we want to ask is that, can we directly understand or analyze these discrete time processes? And another question is, can we develop a general toolbox such that it accommodates both deterministic, such as DDIM, and the stochastic samplers such as DDPN. Okay, so we want to do that in our first part. So before stating our main result, oh, by the way, feel free to interrupt me if you have any questions. So before stating our main results, let's first look at some assumptions. The first assumption is made about this target data distribution. We assume that our target distribution with high probability, with probability 1, is supported on a very, very large support set. Okay, this support can be really large, so this is just put a mild assumption on the target distribution. Okay, so compared to the prior analysis, the prior works usually make assumptions such as log concavity or the smoothness assumption on the target density or target distribution. Okay, the other set of assumptions that we want to make is about your score estimate. So remember that in our, as I mentioned, that once you are given the score estimates, then we can construct those deterministic and this stochastic samplers based on this score estimate ST. Okay, so we assume that you have a good score estimate in the sense that the L2, the average error of the score estimate, is bounded by some epsilon score. Okay, this is like a common assumption made in the prior theory about diffusion models. So notice that this is in the sense of the average, where you're taking the average across the time t and also an expectation over the x. So basically, this means a relatively mild assumption. Okay, and for this assumption alone is already sufficient to analyze DDPM, as I will show later, but this is insufficient for DDIM. So to understand the behavior of DDIM, we would need another assumption, which is to assume that the Jacobian estimation error of your score is also bounded by some epsilon. We call it epsilon Jacobian. Okay, so meaning that your score estimate cannot be too crazy. It needs to have some kind of regularity of your estimate. Okay, so based on this set of assumptions, we are able to show that the probability flow OD or DDIM, which again, we can record it from here. So each yt minus 1 is purely a deterministic function of yt. So once you are given the score estimate, this is already like an algorithm that you can run. So this sampler obeys that the discrepancy or the distance between your target distribution x1 and your sampler y1. This distance measures the discrepancy between these two distributions is bounded by d over t plus some like score estimation error. So notice that here, if you are aiming to find one sampler that has TV distance bounded by some epsilon, then it only requires the t, if you set the right-hand side to be smaller than epsilon, it only requires t, the number of iterations, to be larger than d over epsilon. Okay, so
Can I ask you a question?
Yeah.
How to choose beta t here?
How
Beta.
Yeah, so that's a great question. I will tell you what's the so we have a particular choice of beta t, and the beta t close to 0, it grows exponentially fast and then stay flat. And I will talk about it in a second. That's a great question.
Thank you.
Yeah, thank you. Okay, so and you can see that our bounds is stable with respect to the estimation error. So given estimation arrow, it appears on the right-hand side of this TV bound. Okay, so let's compare our results to some like prior works on DDIN. First of all, regarding our assumptions, we do not require any smoothness or log concavity assumptions on the data on the target distribution. So this is a pretty general. It's pretty general data distribution. And also we have a sharp dependence on D. In a previous result, usually they give you a polynomial dependence on D and without characterizing the exact dependence. Okay, more specifically, the recent paper by Chen et al., they show no concrete polynomial dependence on D, where they are exponential in terms of smoothness parameter because they assume that their density is smooth and they need to exact score function estimate, meaning that you cannot have any error in your score estimate. Okay, where here we allow some score errors. And another paper, which is also a very nice paper, they requires additional stochastic correction terms. So it's different from the DDIM that we studied. For their analysis, they require adding a bit of like noise to their algorithm so that their analysis can go through. Okay, so that's several remarks about this theory. Okay, so back to the previous question, what is the learning rate, right? So the learning rate we adopt looks like the following. So basically, you have you have a set of choice of betas so that our results can go through. But this is common choice in diffusion models where you pick first you have a flat, and first you have an exponential growing, and then you stay flat. So that's the choice of beta t. Okay, due to the time limit, I don't think I will go into details about how we prove this result. But the one key things that I want to mention, if someone is interested, I can talk about this after my talk. Okay, so let me talk about when the set of analysis tool when they're applied to the DDPM type sampler. So recall that for DDPM type sampler, you have again the same forward process, but when you construct the reverse process, instead of only having the deterministic component, each step you will add a new noise to generate YT minus 1. Okay, remember for deterministic sampler, we only have the first part, slightly different in terms of the step size, but similar on the high level. But for DDPM, you add this additional noise. For this set of samplers, we're able to show that the TV distance is bounded by d squared and log factor divided by square root t. Okay, so compared to the previous result, we have d over t, and here you can see we have a worse dependence on the dimension and worse dependence on the iteration steps. Okay, so this means that if you aim to design a sampler that has TV distance smaller than epsilon, then if you let the right-hand side go bounded by epsilon, then it requires your the iteration step to be d to the fourth power divided by epsilon squared. Okay, and well, we are able to accelerate the DPM to get a sharper dependence on epsilon, but I will talk about that later. Okay. So compared to the previous work, sorry, I should mention that we also have additional term regarding the score estimation error. So we need to add a square root d times epsilon score to this result if you have score estimation error. So this result states in the way that the epsilon score estimation error is 0, but I should add that term here as well. Okay, so compared to the prior results where this 1 over epsilon square scaling was previously already obtained using the SDE toolbox, but with a better dependence on D. However, we offer a tool that is completely elementary, where you don't need advanced toolbox such as Gersonov theorem or other more advanced SDE results. So this is basically established by understanding the density ratio and how the arrow propagate along this reverse process. So really, the proof is really elementary. So I can talk about this proof to like a maybe second year PhD student. Okay, so that's when our analysis apply to the DDPM type stochastic sampler. Okay, any question related to the first part?
I have a question.
Yuting.
Uh,
go ahead,
so, yeah, your capital T is supposed to be very large, right?
The
A big
T,
T.
so okay, so it depends on what's your goal, right? If your goal is to make TV to be really, really small, then you require T to be really large. Yeah.
But on the other hand, you just mentioned that you have another term, square root T times epsilon. Is that right?
There is another term which is square root D times
D. Oh, D. Okay, not T.
yeah.
Okay, okay.
Yeah,
Okay,
yeah.
oh, it's okay. Okay, good.
Yeah. That's great.
I was just wondering how much these results depend on that specific definition of that beta T you defined earlier. Is there an effect of it, or because it was pretty specific, so I was wondering if it was needed to be like that.
Yeah, so that's a great question. So the beta T, so from our analysis, the beta T it only works when you choose beta T like that. So
Okay.
these results are established using this specific choice of beta T.
Okay.
Yeah, but yeah, so in practice and in the literature of SE and OD, actually, this learning rates or step size, they're really, really critical. So your results are really, the results that you can expect should be really sensitive to these betas, the choice of beta. So our results only are tailored to this set of choice of beta. And but I want to mention that this set of betas, they are commonly used in diffusion model theory and practice.
Thank you.
Yeah, sure. All right. So if there's no more question, let's move on to talk about our second part on acceleration for deterministic and stochastic samplers. So in fact, in practice, score-based diffusion models, they often suffer from low sampling speed due to extensive function evaluations during the sampling phase. Imagine that you start from some pure noise, right? You want to reconstruct this target distribution. And in each step, it requires evaluating the score function, which is often a large or deep neural network. So each time it requires you to evaluating that deep neural network. And it usually takes hundreds to thousands steps to go from the pure noise to a target distribution. So in practice, these diffusion models are often uh, a slow sampling method compared to the GAE or a GAN or variational autoencoders. So in fact, if you want to use DDPM to generate 50K images, and this image, you can see the size is not particularly large, it's a moderate image size, it takes 20 hours compared to the GANs usually take like 1 minute to generate those the images. So this is a reason why diffusion models, they often suffer from this drawbacks. Okay, so to overcome this issue, people have proposed several ways to speed up diffusion models. One prominent example is based on this notion called distillation. The distillation tries to distill information, distill a pre-trained diffusion models into a smaller size model that can be executed rapidly. Okay, so this is actually a very, very interesting and popular idea in practice. And recently we have developed some mathematical theory to understand this distillation or consistency training, which is another name similar to the distillation. Okay, so this is one approach, which is a training-based approach, where you need to train by, so given pre-trained models, you need to do additional training in order to extract information to get into a smaller model. Okay, another popular idea is this training-free idea, where you want to directly use your pre-trained diffusion models, particularly the score estimates, for sampling without any additional training. And hopefully by designing the data generation algorithm more clever, then you can shorten the sampling time. Okay, so the question that we want to ask here is, can we design a training-free determinate sampler that converges provably faster than the previous DDIM? Just based on our pre-trained scores, can we just modify our data generation mechanism such that it runs faster? Okay, so that's the question that I want to ask in the second part. Well, so in fact, we can design accelerated version of our DDIM. So the algorithm works as follows. So we will compute a midpoint yt minus. This is a deterministic function yt where, well, let me tell you. So phi of yt is a deterministic function of yt given your score estimate. So you first compute this midpoint, we call it yt minus, and then use this result to update our yt minus 1, where this yt minus 1 is again a deterministic function of yt and yt minus. So this paucity here contains the original DDIM function, if you still remember this function, plus some momentum-like term. So it only based on the pre-trained score function. So you do not need to train your model again, but you just use the pre-trained score function, evaluate at yt and yt minus 1. So that gives you, again, a deterministic sampler. So the only thing you need to modify is first to compute this midpoint and then add this momentum-like term in your sampling phase. Okay, so it turns out that we can show that this new sampler works provably faster than the original DDIM. Okay, so let me first show you some results on the acceleration phenomenon for our new sampler. So here in the first row, I show you the performance of DDIM, where the first image, where this from the left to right, I fix the number of function evaluation from 5 times to 50 times. As you can see for DDIM, once you increase the number of function evaluation, it gives you clearer and more high quality samples from left to right, right? And here I compare our new sampler with DDIM. Also from left hand to right, I fix the number of function evaluations and look at the image that our samplers gives us. You can see that, for example, you fix the number of function evaluations to be 8. Comparing these two images, you can see our sampler give you a clearer and higher quality image compared to DDIM. Right. So, right. So this is another set of examples. You generate, other than churches, you generate bedrooms and human faces. And you can see there's always an improvement given the number of function evaluations. We have a crisper and less noisy image generation. Okay, so it means that it actually gives you a better or faster sampler by adopting our a little bit more complicated algorithm, but it runs faster in practice. Okay, so to show you the theory around our sampler, first let's recap our assumptions. Let's focus on DDIM. So we need the Jacobian estimation error as this epsilon Jacobian. We assume that the score estimation error again is bounded by some epsilon score. Okay, we assume that our target distribution lies on this like a compact large support set. Okay, so we are able to show that our accelerated determinist sampler obeys the following property, where you have the TV distance, measuring the quality of your sampler is bounded by d to the 6th power divided by t squared plus some estimation error, score estimation error. Okay, so the second part, these parts are similar to our previous results on DDIM. Okay, so you can see now that the leading order, the first term, depends on t squared instead of 1 over t, right? Remember that for our previous theory on DDIM, the TV distance is bounded by d over t, where we get a t squared dependence. So if you compare these two results, you can see at least the upper bound, we have like a smaller or faster dependence on t. Okay, so again, this result is stable with respect to errors in your score estimation error. We have like a very general assumptions on data distributions. Okay, is this result clear? Okay, so about this d dependence, this is not ideal that we have the d to the 6th power. We believe that using a tighter analysis framework, we can sharpen this dependence to d to the 4th power, but this is still ongoing work. Okay, so you can ask what's the sharpest or most sharp dependence on this d? And can we improve it to be like a linear in terms of d? That part I don't know yet. All right. So if this result is clear, maybe let me give you some intuition on how we design our acceleration scheme. Okay. So in fact, this acceleration depends on or is designed based on the rationale of high order discretization. Okay, just to give you some ideas. Firstly, recall our forward process. We gradually add noise to our data and diffuse the target distribution. And if we write a general form for this forward process, you can see that we can introduce this parameter gamma, which is a number between 0 and 1, and denote x gamma in the following. So this is like a combination of your target distribution and the random Gaussian noise. Okay, so now you can see that this is like a continuous version of our previous forward process, because for that we only like define it on discrete time point of this alpha t, alpha 1 to alpha capital T, but the gamma can take any continuous number. Okay, so a key relation between x alpha t minus 1 bar to x alpha t bar. So this is like a more complicated notation, but what I mean is that this is just xt minus 1 to xt. So when you go from xt minus 1 to xt, key observation is that it can be written in this way. So basically, once you know the score function, you can recover xt minus 1 by doing this integration over the score function plus the xt. Okay, so this relation, you only need doing some like a derivative and doing some integral, then you can like establish this relation really easily. Okay, so for now, please just believe me that this is true. We go from xt minus 1 to xt minus 1. Okay, so so the probability flow ODE satisfy this equation. Okay, so now because this is a you are doing integration from alpha t to alpha t minus 1, right? But in practice, we only estimate those scores on discrete time points. So we need to approximate this integral using some approximation using the discrete time estimate. So if you directly taking the integral and pretend the score function stays flat or stay as a constant during the integration, and let this score function to be directly equal to some st at xt at xt, which is a score estimate at time t, and pretend that this is just a constant. So when you do integration, this boils down to a very simple formula, right? This is just a constant times the length of the of this interval, and then you recover the original DDIN. All right, but just letting this to be a constant and then plug this in, then you recover the original DDIN. So you can imagine that if we can approximate this score by a more refined approximation, for example, using a Taylor expansion, expand this using at the endpoint and take the derivative, right? So this is just a one-order Taylor expansion. If we use this Taylor expansion and plug that in, then that gives you our accelerated version. Okay, so that's the rationale under our design of our acceleration paradigm. Okay, just doing a first order Taylor expansion for your score function, that gives you our sampler. So, all right, so this is, I want to mention, similar in spirit to the DPM solver by Lu et al. If you are interested in this, I refer you to this nice paper here. All right, so that's I want to say about the DDIM acceleration. So in fact, we can also design a stochastic version for DDPM, accelerated version for DDPM. Similarly, firstly, we introduce this phi t, which is just a deterministic function. Well, not exactly. So this phi t is both depend on YT and a random noise ZT. So you can plug in this phi t function, very simple function. And this psi t is defined as, once you compute this midpoint YT plus, and then based on this midpoint YT plus and additional Gaussian noise, we can construct YT minus 1. So the function of psi t is exactly the same as DDPM. So what we did is just that instead of directly plugging YT, we first compute YT plus, that's midpoint, and then plug into the same function. Okay, just doing this additional injecting noise, just injecting this additional noise, we're able to get an accelerated version of DDPM. Okay, and here it only requires one score function evaluation per iteration because we only use the score function once in this algorithm. Okay, it turns out that now we have a better dependence on t again. So compared to the DDPM, the previous result on DDPM, we have a square root t dependence. Here we get a t dependence. So we get a faster convergence for the accelerated version. Okay, so again, this result, if your goal is to find an epsilon accurate sampler, you only need 1 over epsilon times poly d dependence and the iteration complexity. Okay, so that's our okay, so to tell you a little bit more about how we design this acceleration scheme, so the intuition is again a higher order approximation, but unlike the DDIM, we use a first order Taylor expansion for the probability flow ODE. Here we need to because this is a stochastic version, so we need to approximate this conditional density via like a refined approximation. Okay, so I will not go into details about this, but this shares similar intuition as before. Okay, so to summarize, what I tell you in this talk is that we develop a non-asymptotic theory for both DDPM, the probability flow OD, DDIM, and DDPM, although the results on DDPM already established via more advanced SDE toolbox. So here we offered a kind of elementary proof, elementary toolbox, so that everybody can work on DDIM, DDPM, and get a sharper rates for DDIM. Also, we develop new schemes to accelerate both DDIM, DDPM. Okay, so as several future directions, we are interested in how to get better dependence on the problem dimension D. Also, we think that acceleration via high order approximation for ODE or SDE could be a very, very interesting direction to pursue. And in addition, as I discussed, we sort of decouple the score learning and score matching part with the sampling generation part. Can we put them together and develop an end theory to account for both phases? Okay, so with that, I conclude my talk. Thank you everyone for